5 panelists with us today, and we'll introduce them one by one shortly. But perhaps before that, a couple of words as to the importance of the subjects and what we want to achieve today. As you all know, both climate change adaptation and disaster risk reduction are increasingly on the radar screen of decision makers, with climate change impacts being on the rise and felt increasingly across the globe. Adaptation is becoming an urgent issue for planners, for developing and developed nations alike. Similarly, the disasters are increasing. 2011 have been the year with most impacts on disaster globally, and that has really put more urgency for planners to deal with the issues and try to reduce disaster risk in the first place. And we're increasingly seeing, certainly in the international policy arena, but also at national levels, given the similarity of both issues, an interest by the government's decision makers, but also on the private sector, on how to deal with these issues in a synergetic way. So that's why what we wanted to talk about today. We wanted to show you some examples of how ecosystem considerations could be dealt with in both areas, climate adaptation and disaster risk reductions, given that the conservation community is actually trying to promote nature-based solutions to both issues. But we also want, and I hope that in the discussion we can dig deeper into some of the challenges and opportunities, such as quantifying the disaster risk reduction services of ecosystems, and how do we go about convincing decision makers and actually mainstreaming this in development planning, and how can we foster better coordination. I think you have some papers with the agenda and some focal questions that we want to raise later. So without further ado, we can start. Sorry, I'm just missing one. With our first speaker today, Dr. Steve McNulty, who's the team leader for the USDA Forest Service Eastern Forest Environmental Threat Assessment Center. Steve has over 20 years of experience in assessing global climate change and ecosystem at the landscape and continental scale, and he has chaired and served on many international assessments on climate change impacts, including the Climate Change Science Advisory Committee of the USGS Climate Change Science Program. So, Steve, without further ado, the floor is yours. Thank you.
Thank you. All right, thank you. We're going to do a series, as was mentioned, of talks that are going to lead up to a panel discussion at the end. And so what I'm going to do is start with looking at the role of ecosystem science and tools for regulating disasters and supporting climate change adaptation. Now, the way I'm doing this is I'm going to do this from about 30,000 feet. So the idea with my talk is that there's a series of 8 questions, and these questions are designed to look at it in a very broad context. So hopefully, as I present this, you'll see how this relates specifically to your issue or area of research. I decided to use this background today for my talk presentation. This is actually a dust storm that we were having a couple months ago in Texas, where it's been exceedingly dry there for several years, including this year. And this is a pretty typical event these days, where we're having these dust storms, and this is the middle of the day, and it looks like almost midnight. So there's not a lot of good things about climate change, but maybe one of them is it makes nice background colors to use. So with that, we'll get started. So question 1. What scientific evidence exists for quantifying the role that ecosystems play in regulating, and the key here is regulating, disasters and other risks associated with climate change? Now, there's really 3 ways you can regulate something. You can preserve something, and in preserving you try to prevent negative disasters. You can destroy something, and in doing that you may create disasters, or you can modify an ecosystem. And who's to say what's going to happen once you modify these ecosystems? So what I'm going to do with this first question is look at all three perspectives of that situation. So the first one is, there are many examples for the destruction of ecosystems creating or contributing to disasters. This is by far the most common form of how the regulation of ecosystems is perceived. So in recent history, we have things such as the Ohio River fires back in the 1960s, where the pollutant loading on these ecosystems were so bad that the rivers literally caught fire. A lot of work in acid rain in the 1980s in Europe and in the United States, where we had all kind of negative impacts such as fish kills, nitrate leaching, forest mortality. This is a function mainly, again, of deposition of pollutants, the acidification of these ecosystems having negative impacts on ecosystem health. Deforestation leading to rapid surface flow and sedimentation and flooding. This goes way back. This probably goes back to ancient Greece and the UK and Ireland, where massive harvesting of the forest then created flooding. We certainly have seen it in the United States, in the Allegheny Mountains back at the turn of the century, where all of the cutting of the woods would lead to mass soil erosion, sedimentation of the streams, and subsequent flooding. Deforestation leading to patterns in weather shifts. We've seen it in the Amazon, we've seen it in the Congo, areas where large portions of the forest are removed, and in turn this changes the shifts in weather that we see at a continental scale. And of course, most currently what we talk about a lot is climate change. Not only the acidification of the oceans and the loss of the coral because of the CO2 in the atmosphere, exaggerated drought, exaggerated flooding. There's a long list associated with climate change. So these are the kinds of examples where destruction of an ecosystem contributes or leads to a disaster. There's also other examples where there are negative impacts from seemingly good management actions. So the best laid plans of mice and men do often go astray. Examples, kudzu in the United States. It was imported from Asia, used to control soil erosion, or so we thought. It became an invasive species and overtook many other ecosystems. The U.S. Army Corps of Engineers is notorious for its modification of ecosystems, such as developing levees on the Mississippi River. These are areas that parallel the river and they keep the water in, they channel it. But what happens when you channel it, instead of water going off in the broad areas, it's concentrated, and in those areas you have mass flooding. Channeling of the Everglades, where we drain the Everglades for agriculture or other purposes, and in turn we destroy the Everglades and have negative impacts with that. Reduction of soil fertility following the construction of dams. So Aswan is just one example where where the dam was constructed. Previous to that, there'd be seasonal flooding, increased soil productivity of those flooded areas. After the dam was built, the flooding stopped, productivity decreases. The Forest Service, who we work for the last 60 years has advocated the reduction of wildfires. Anytime they saw a wildfire, they put it out. But what's happened over that 60 years is we've accumulated a lot of fuels, a lot of wood in the ecosystems. Now with climate change, we're seeing these mega fires, these fires which are massive. Historically, they would have been a fire, they would have burned an area, they would have gone out. Now these are fires that we read about in the paper, in the news, where they're destroying whole communities in combination with climate. Reduce stream flow in semi-arid areas where we're trying to do reforestation. So the idea is that trees are good, we want to plant them there, but in planting them in some areas we may be draining down the groundwater table or reducing stream flow. All good intentions originally, but in this management they've had negative impacts. So let's go to the last example where preservation of ecosystems is preventing negative impacts. This is really what the topic of this talk was supposed to be about, but the problem is it's very difficult to assess a non-impact of something that didn't happen, right? So how do we talk about this was great because it didn't happen? Well, it probably did, it probably helped, but that doesn't make the newspaper, that doesn't make a study. So what we end up doing is talking about the opposite. We talk about the impacts, not the prevention of impacts. even though ecosystem restoration is much more costly than ecosystem preservation. So what we do is we wait for something to become degraded, and then we try to restore it. This is probably the least effective, most damaging way to look at ecosystem sustainability, but unfortunately, it's the most common. So the take-home point number one is its high cost to restore and high impact of loss is the worst case scenario, but it's also the norm. So this is how we currently go about business. We wait for something to be destroyed, whatever it is, and then we go back and try to fix it, as opposed to trying to preserve that ecosystem under climate change, under other disturbances in the first place. This is a hard sell, but it's really more cost effective. Question 2. What are the major information gaps in understanding how ecosystems and land use planning can contribute to disaster reduction and climate change adaptation? So what don't we know? Where are our big gaps of information that prevent us from doing some of this planning? Well, broadly defined, I'd say there's 3 types of areas. The first one is gaps in historic understanding. So this is what happens when we cut all the trees down? What will happen to an ecosystem? Well, we can pretty well guess that. That's a minor issue. You know, if you cut the trees, you're going to get increased erosion, you're going to get increased rapid stream flow, a whole bunch of things that we've studied for a long time and we understand pretty well. Then there's gaps in future change. Well, that's true. We understand about how historically that works. What happens with climate change? How could that alter in the future? That's called a moderate issue. I'd say there's some things we don't know about it, but not a lot. The final one is gaps in our understanding of the synergies. That is, how these things work together now and in the future. That's a major issue. And I am going to invoke the good name of Mr. Donald Rumsfeld, who, if you're old enough, you may know this person. He is not an ecologist, for those who do not know him. He was the former Secretary of Defense of the United States. And back in 2002, Mr. Rumsfeld had a quote which wasn't very well received in the news media, but was truly a profound quote. And it directly relates to this talk. So let me read it as best I can verbatim. As we know, there are known knowns. That there are things we know we know. We also know there are known unknowns. That is to say, we know that there are some things we do not know. But there are also unknown knowns. The ones we do not know, we do not know. Yeah, see, we're laughing, but it's true. There are things we don't understand and we can study, and then we'll know them. There's some things that we don't know, and then there are things we already know. But there are things that we're not even looking for. The ones that we don't know, we don't know. And these are the major issues, and these are the most serious issues. So the take-home point for number 2 is that the uncertainties that will have the greatest impacts are those which we're not even considering the impacts. So when we talk about uncertainties, what's the uncertainty of having a 100-year flood in the next 3 years? There's an uncertainty associated with that prediction. But what's the uncertainty of having not a 100-year flood, but having this whole area underwater in 3 years? We're not really thinking about it because there's nothing in our historic observation that would suggest that would ever happen. But what if it did? What if it did? That's an unknown unknown. Let me give you 3 brief examples of unknown unknowns that we've recently seen. One is the mega fire hot scorching. As I mentioned, they're having a severe drought in the Midwest right now. And in that area, there's forests that have 2 stories. The lower story of the forest is comprised of cedar, which is very flammable. The upper story is composed of pine, which is less flammable and generally has a bark that is resistant to fire. Well, what's happened in those areas is that normally the cedar would burn and the overstory pine would be fine. But because the fires have gotten so bad there and so large, they're having crown fires. And what this means is that the fires are going across the tops of the trees. So instead of burning the understory like it normally does, historically, it's burning the tops of the trees. And so the tops of the trees are dying, and these lower understory, more flammable species aren't dying. No one ever thought of that. No one thought that would be possible until it started to happen. Another example are the extreme droughts in the bottomlands. In other areas, they're having these uplands and bottomlands. The uplands are more droughty and they look kind of ragged and not very healthy. The bottomlands are these areas with a lot of water, very rich, high productivity, never have drought problems until now. Now what's happening is the drought's getting so bad that these streams are drying up. So the forests that used to be really resistant to drought are the first ones to go because they're not used to drought. They're used to always having that water. Whereas the upland forests, which are kind of always scraggly and struggling along, they have deep root systems. And because of that, while the drought's going on, they're surviving. The scraggly, crummy trees are surviving, where the bottomland trees are dying. No one thought of that. That's an unknown unknown. The final ones are bugs and spruce. Similarly, we're having these issues in the mountains where it's getting warm and hot and dry, and up in the high elevations of the mountains are spruce trees. And normally what happens up there is these beetles can't get up that far. But because it's so hot and so dry, the beetles are getting into these upper elevation forests. And in those forests, some of these trees are scraggly, they're not on good sites, they're real rocky, they don't look very healthy. And other trees are in perfect soil, they get a lot of rain, they look really healthy, fast growth. And what's happening is the beetles are coming in, and the beetles are killing the trees which used to be the most healthy, and leaving the scraggly trees. So when you go up there to find out why, we find out that those healthy trees have big crown masses, a lot of leaves, and not much roots, because they don't need them. They have all the water they normally need, they have the nutrients, they don't need it. Whereas the scraggly trees have very limited resources. So when the drought comes, the beetles kill the healthy trees because they dry out, they can't produce resins to get the beetles out, and they die. Whereas these scraggly trees keep going. Nothing we ever saw would predict that happening, but we're seeing it more and more. So under these extreme conditions of climate change, we're getting more and more unknown unknowns occurring on a daily basis. So question 3. How much uncertainty is associated with understanding how ecosystems contribute to these risks? Generally, I would say that uncertainty is inversely proportional to our level of understanding. So the more we know about something, the less uncertain we are about it. And let me give you 3 examples of this in the context of our knowledge gaps, which we talked about in question 1. Historically, if there's a steep slope that's logged, the risk of landslide relative to an unlogged area is pretty little. So we know that there's little uncertainty. If you cut down the trees on a hill, you're probably going to get more erosion. However, if that changes with climate, that uncertainty may go up because we don't understand climate change as well as we understand historic conditions. And finally, if we go back to that unknown unknowns and these interactions of forests, in the future, our uncertainty becomes major. So for example, in the future, if CO2, as it continues to increase, changes the amount of roots that a tree has relative to the amount of leaf it puts out, that'll change its ability to soil erosion and to landslide capability. So the risk increases with increasing susceptibility and our lack of knowledge. So how much uncertainty is acceptable in the context of planning and practice? You know, if you looked at just a strict cost-benefit analysis, the way economists do, you might say, well, we get a lot of benefit from this for a relatively little cost, so we should look at it using this much money, this much effort to understand that risk and that uncertainty. It might be a one-to-one relationship, or it might be very costly to understand the benefit of better predicting that uncertainty. But in reality, that's not how things work, at least for ecosystem studies. Unacceptable consequences are near zero if you have a priceless treasure. And these are some examples: the Mona Lisa, the crown jewels, the US Constitution. So that level of uncertainty is near zero. You want no uncertainty as to risk for damaging those sorts of things. However, in ecosystems, it doesn't work that way. We seem much more willing to allow risk in ecosystems. I think probably the largest example of that is climate change in our planet, right? We are changing the planet profoundly, but we're willing currently, as a planet, to accept that level of risk. And so the uncertainty about those ecosystem impacts have not been considered because ecosystem impacts have not been considered. So we can't assess the uncertainty until we assess the impacts. And we're unwilling to assess the impacts, getting back to question 1, until after the impact has happened. So it's kind of a catch-22. So the take-home point for these last three questions are, ecosystem impacts are often not addressed, let alone uncertainty around those impacts. So until we can talk about uncertainty, we need to start doing ecosystem impact assessment. Question 6. What role does biodiversity play in supporting resilience to disturbance? Well, at an ecosystem level, generally, increased biodiversity stabilizes resilience. For example, in a mixed species ecosystem compared to a simple ecosystem, if you lose a single species, there's less risk of having a very different or a very negative impact. So if you only have 2 or 3 species in an ecosystem, you lose one. The impact for that ecosystem is generally expected to be much more than if you have 100 species in that ecosystem. However, I think it's ironic to note that it's also true that highly competitive, often invasive species can disrupt complex ecosystems on their own. So you can take a very complex ecosystems and you can add a single species like kudzu or purple loosestrife, and that will take over that entire ecosystem if it's invasive. So you can't say that it goes both ways. It seems to be that a single ecosystem or a single species ecosystem can have a much greater impact if it's added than if it's